So today we're going to focus on reviewing the first half of the EMR unit. We have a unit exam that's coming up in a few days, so I want to make the most of this time right now to make sure that we're understanding all of those early concepts from earlier on in this unit. So the unit exam, as I mentioned, is on Thursday this week. We're going to get some focused review of the first half of EMR today. This is going to be another one of those you try, I go over lessons. I think those are the most like bang for our buck. So tomorrow's lesson, just by the way, is also going to be just like this. But how it works is I'll post a question, you give it a try, I'll go over it. So in other words, in this video, you'll just have to pause the video once I finish reading the question and then give it a try, unpause the video and see how I went over it, make sure that you were able to get it right. If you're consistently not getting these questions right, that's where you have to reach out and let me know. We can have a Zoom meeting one-on-one if you need. We can send emails, you can use Remind, whatever you need to do, and I'll get you caught back up because it's important we understand this stuff before we have that unit exam. Now recall that the first half of the EMR unit covered a whole gauntlet of things here. The first thing was speed of light, which included experiments to measure the speed of light. Most notably, the one you really need to know is the Michelson one. We're going to do a question like that today. Reflection off flat surfaces, refraction in different mediums. The different mediums one is quite interesting. That's where like light goes through, let's say, water, or it goes through ice, or it goes through a diamond, or whatever, and different properties of the light changes as it goes through that medium. The other things we've got to talk about are curved mirror reflection as well as curved lens refraction. Those ones were the ones that really gave us a lot of trouble, especially the diagram ones. And yes, you will be expected to draw a diagram. We'll do one of those today as well. Anyway, I'll stop rambling on here. Let's get started. Question one: in a Michelson-like experiment, a 12-sided mirror rotating at 38,400 RPMs is placed 19.0 kilometers away from a fixed mirror. Determine the speed of light as calculated from this experiment. So in other words, don't assume the speed of light. We're calculating it this time. Pause the video, give it a try, and I'll go over it. So first things first, I like making a little bit of a data bank here. The frequency, of course, is 38,400 RPMs. That means rotations per minute. Now, RPMs aren't the standard unit for frequency. We prefer rotations per second, or in other words, more commonly known as hertz. So if this is how many times it's rotating per minute, to find how many times it's rotating per second, you just have to divide it by 60, and that's going to give you 640 hertz. Now, the other thing we know is that it's a 12-sided mirror, which is going to be useful because, remember, in a Michelson experiment, we only want it to rotate one side. So in other words, we're not going to rotate in a full circle. We're going to only rotate 1/12 of a rotation. So let's put it this way. Since this is the frequency, that's how many times it rotates in 1 second, you can flip that around to find the time that it takes. In other words, the time period it takes, so the time it takes to rotate just once. That's just the reciprocal of it, of course. It's 1/640. So 1/640th of a second is how long it takes this thing to rotate one full circle. Again, we don't want it to rotate one full circle. We only want it to rotate 1/12 of that. So I'm going to take this. See, I'm not even calculating it as a decimal quite yet. I'm going to take this, though. I'm going to divide it by 12. This is going to tell me how long it takes to make 1/12 of a turn. And throwing this in my calculator gave me 1.30208 times 10 to the negative 4. And that's in seconds. So again, this represents how long it takes to rotate 1/12 of a turn. Now the other thing, because we now have the time, the other thing we need to use to find velocity is, of course, the distance. Well, we know the fixed mirror is 19.0 kilometers away, but keep in mind in this experiment, you have your like multi-sided mirror. Obviously, that's not 12 sides, but you get the idea. You have your multi-sided mirror, and then some distance away, you have your fixed mirror, right? So these are 19.0 kilometers apart, but keep in mind the light, which is originally generated right near the rotating mirror, has to reflect off of this and then reflect off the mirror and come back in the time that it takes this mirror to rotate 1/12 of a turn, right? So in other words, this distance isn't the actual distance. You got to times it by 2. So distance is 19.0 times 2, which is 38.0, but that's in kilometers. So let's change that very easily to meters by timesing it by 1,000. Anyway, so now we have our distance, we have our time. That's all we really need, right? The speed of light can just be found using distance over time. So V is d over t, or in other words, V is equal to 38,000 divided by 1.30208 times 10 to the negative 4. And if you throw this in your calculator, you're going to get to 3 sig digs, 2.92 times 10 to the 8 meters per second. And yes, it is 3 sig digs here. I can imagine some people saying, well, wait a minute, there was 12-sided or 12-sided mirror, right? So it's just 2 sig digs there. This isn't actually 2 sig digs. Something we haven't talked about since I think literally the first week of Physics 20 is if you're ever given something that is like a clear exact value, it technically has an infinite number of sig digs. There's no way you can have like an 11.4 sided mirror or something, right? So 12-sided mirror, that has an unlimited number of sig digs just right there. So no, it's not 2 sig digs. It's the next lowest, it's 3, okay? Anyway, moving on. All right, given the following scenario, determine the angle of reflection theta. So theta is this guy right over here. Pause the video, give this one a shot. All right, now we're gonna go over this one. This one's not so much a physics question, it's almost more like a math question. I was almost not gonna give it to you, but I thought, you know what, might as well. Basically how this works is, remember, off of a flat surface, reflection is gonna come off at the same angle that it hit the mirror at, right? So in other words, we know right here, this angle from the normal is going to be the same as this angle from the normal. So right here, it's going to be 55 degrees. Now, another thing is this is clearly forming a 90-degree angle as per the definition of a normal line with the actual mirror surface here. And a 90-degree angle we can use to determine this missing little piece right here. So 90 minus 55 is 35 degrees. It's 35. It's really small written, but whatever. Now, the next thing you can notice is there's a triangle that forms right here. And hopefully you remember from math that all triangles have a sum of interior angles of 180 degrees. So in other words, if we just take 130 and 35 and take it away from 180, you can find this angle down here, which is going to be 15 degrees. Now, once again, with this normal line, they're going to add up to 90 degrees. So that means this angle is going to be 90 minus 15, which is 75 degrees. And of course, because of how reflection off of a flat surface works, that means theta, might as well write it over here, theta is therefore equal to 75 degrees. Anyway, moving on. Question 3, a ray of red light with a wavelength of 730 nanometers travels from air into vegetable oil, which has n equals 1.47. Remember, n is the refractive index, in case you're not aware, at an angle of 40 degrees. Determine the wavelength of the light as it travels through the vegetable oil. What type of light is it? I even threw that chart in there to help you. Pause the video, give it a try. All right, so I'm going to go over this one now. Let's just take a quick inventory of what we got here. We have the N of the vegetable oil. Since it's going from air into the vegetable oil, that's going to be our second N. So I'm going to say N1 is N of air, which is just 1.00. Therefore, N2 is equal to 1.47. Now we know the light is red and has a wavelength of 730 nanometers. We can assume that was in air, so I can say that wavelength 1 is going to equal 730 times 10 to the negative 9 meters. And we're looking for the wavelength of the light as it's going through the vegetable oil. Well, that would be lambda 2, your wavelength 2, which is our unknown here. This angle, believe it or not, is actually unnecessary because if you look at your formulas, there is a formula. It's that whole long strand that has like 4 different formulas all built into it. But if you kind of pick and choose the ones that use these variables, you can see that N2 over N1 is going to equal lambda 1 over lambda 2, okay? Very careful with this. I remember there were a lot of people who always thought it was like N1 over N2. Like there's a lot of people that were making that common mistake. It's not. Take a look at your formula sheet. It's N2 over N1. It's the odd one out. All the other ones are 1 over 2. That's just how it works. Anyway, throw the numbers in there. N2 is 1.47 over 1.00. And then lambda 1 over lambda 2, that would be 730 times 10 to the negative 9 over our unknown lambda 2. To find lambda 2, just multiply it over and then divide the 1.47 over. This divide by 1 here is doing nothing at all, so you might as well ignore it. So bottom line is lambda 2 is going to equal this divided by this, which will give you, I have it written down here. Okay, in your calculator, it's going to say something like 4.966, I think I just rounded it to, times 10 to the negative 7, which might be a little weird for some people to interpret, but just remember, when you're timesing by a negative or 10 to a negative number, that just says your real answer is going to have to move your decimal to the left more. Well, keep in mind in terms of wavelengths, we like it in nanometers, which is times 10 to the negative 9. Bottom line is we can just move this to the right a couple more, and then we can just add 2 onto this, right? So we can say that lambda 2, and I'll even round this just to 3 sig digs, is 497 times 10 to the negative 9 meters, or in other words, 497 nanometers. According to this chart, 497 just barely falls within this range right here. So the light would be green. There we go. So those right there, that would be your answer for your wavelength as well as what type of light it is. Now, just in case you're wondering, because like even when I saw this question, I was like, that just doesn't sound right. When you're like, if you beamed like a red laser into vegetable oil, is it really going to turn green? Well, actually, like, I'm sure none of you are surprised by this, but I actually gave this a try. I have like a little red laser here in my apartment, and I gave it a try with some vegetable oil I had. Now, the one thing that you just need to understand, and I kind of knew this even going into my little experiment, is that the wavelength of the light is only green while it's within the vegetable oil. Now, vegetable oil isn't like smoky air where you can actually see a beam of light as it travels through the surface, right? So when I beam the laser through the vegetable oil, it doesn't actually look like there's green light in it. Matter of fact, it looks like there's nothing in it, and the red light just comes straight out the other side of the vegetable oil container. Now, by using an angle, of course, you can influence the final angle of it as well. But just keep in mind that no, when you beam a red laser through vegetable oil, it's not going to come out green, but within the vegetable oil, if there was some way to determine that, it should actually theoretically be green. I wonder if you like took a piece of paper or something and then stuck it in the vegetable oil and then like tested that. I'm not going to advise doing that, especially during this whole, situation going on right now, because vegetable oil is hard to find. So I'm not going to waste my vegetable oil by doing that. But you know what? We're going to move on. So question 4. Oh, you can already tell. I can already hear some of you guys cringe. It's a curved mirror question. Ooh, here we go. So a 5.00 centimeter tall object is placed 8 centimeters away from a convex mirror with a focal length of 10 centimeters. Determine the characteristics of the image. So in other words, the magnification, attitude, position, and type using a diagram. You can tell I'm recording this on a Monday. Anyway, determine all those characteristics using a diagram. Give it a try. We'll go over it in a second. All right, so we're going to go over it now. I'm going to try my best on this. I actually drew it on a piece of paper, and I was thinking I could just take a photo and then plop it in here, but then I thought, no, you know what? That's cheating. I'm going to suffer through the process just like you guys did. So this is our focal length right here. Keep in mind we're using a convex mirror, so we need to be using this side as our actual reflective surface. I just want to make sure I get my dots correct on the other side, so I'm going to estimate that distance. That looks like it's about right for an equivalent to F, and then therefore the 2F equivalent. I'm actually just going to no, I got to sit back a little bit. I'm sitting too close to the computer. I think it's a little closer than that. There we go. That looks better. Okay, and then there's about 2F. Okay, we just got to make sure we get things accurate. Of course, if I had a ruler, it would be a lot easier. Please use a ruler on these ones. Anyway, so let's draw all of our stuff. We know the focal length is 10 centimeters. So it's 10 centimeters. Our object's going to be 8 centimeters away, so it's going to be somewhere about right there. And it's only 5 centimeters tall. So I'm going to draw it like this. That looks about right. That looks like it would be about 5 centimeters. 5 centimeters would be half of this. Yeah, it looks about right, and that'd be a distance of 8 centimeters away from it. Looks pretty good if you ask me. That's not too bad. So I'm just going to quickly change pen color here to draw my rays. Just change to blue. Remember, there's 3 rays that we have to draw, and they all originate from the tip of the object. Okay, where all of the light rays intersect is going to be where your image is going to form. Now, the first ray I always draw is the one that's parallel to your line right here. And when it's parallel to the line, after it strikes the mirror, it's going to bend in such a manner that the light ray would go through the focal point. Now with convex, of course, light isn't literally going to be able to go behind the mirror into that focal point. So what happens is you have to draw a dotted or dashed line to represent that. Anyway, so let me draw my flat line. Again, please use your ruler. This is going to be really rough. And then, of course, once it strikes the mirror, it then has to reflect through the focal length, but of course light can't literally go behind the mirror, so I'm going to draw a dotted line from there instead. There we go. That's not too bad. Just fill in the dots a little bit more, and then just to make sure you're really clear as to where that light's going, it's going to be reflecting back that way. Good. All right, next one. You draw a line from the tip of your object again through the center of curvature. And when you do that, it's going to bounce straight back. Well, the center of curvature is way over here, okay? So this one might be a little tougher for me. I'm actually gonna literally get a straight edge and hold it up to my computer just to help me out here. Okay, I can kind of see where it's gonna go. Again, I can't, I've tried before putting on the trackpad and it really doesn't work too well because I can't see what I'm doing. But it looks like it's gonna go something like this. And then I'm gonna stop that line there and I'm going to make it dotted now. Keep it going, keep it going, keep it going. It's not perfect, but it's all right. There we go. And just for fun, we'll even continue it off this way. Good. Okay, anyway, so that light ray needs to go through the mirror and then through the center of curvature. Good. All right, now our last one. It's a bit of a weird one. It has to go from the tip of the object through the focal length, and once it strikes the mirror, it's going to bounce back parallel to your parallel line here, right? So in other words, I'm going to use my ruler up against my monitor again. My light ray needs to be drawn kind of like this. I'm going to stop it there, and then I'm going to keep it going. Oh wait, no, I'm not going to keep it going. My mistake. Sorry, ignore that. Once it strikes the mirror, what is it supposed to do? Oh, it's supposed to go parallel. So it needs to bounce back out this way. And then on the other side of the mirror, we have to carry that forward. There we go. That makes it a lot more clear where we're intersecting now. So remember, after you strike the mirror, your virtual lines are going to behave as your real ray would behave, just behind the mirror. That's all, right? Now, we can clearly see where all of these little dotted lines are going to intersect. If they had intersected on this side, that would have been fine. But of course, with a convex mirror, in case you haven't remembered, convex mirrors will always produce a virtual image. And virtual images, of course, are where your dotted lines all intersect. So it looks like the dotted lines are intersecting somewhere around here. So I'll draw my image. I'll even label it. There's my image. This was my object. And I think now it's pretty clear how we can get our characteristics. So our magnification, first of all, it very clearly is smaller. So there's my magnification. Attitude is just how is it facing? Well, it's going upright. Position, well, position is relative. Remember, this point on a mirror is called the vertex. So I could say position, it's between F and V. That works. And then type means real or virtual. Well, it's behind the mirror and it's with the dotted line, so it's going to be a virtual image. There we go. All right, one more question. Next one, an object 6 centimeters tall produces a virtual image 6 centimeters from a convex lens. If the focal length of the lens is 4.0 centimeters, what is the magnification of the object? I would highly advise doing this one mathematically. I'm not even sure if a diagram would really work unless it was absolutely perfect. So pause the video here, do this one mathematically, give it a shot. All right, so I'm going to go over this one now. This one's a little bit beefier. It takes a little bit longer. There's a lot of formulas going on, but if you keep track of all your variables and you make sure that you use them positive or negative correctly, you won't have too much issue with this, hopefully. First things first, a convex lens. Lenses are opposite of mirrors. A convex lens is also known as a converging. And remember, converging, whether it's with a lens or with a mirror, has a positive focal length. So this focal length is indeed positive 4.0 centimeters. Okay. Now the other thing we need to watch though is this this fact that it's a virtual image. Virtual images have negative distances. Okay, so the distance they are from the mirror or from the lens in this case is going to be a negative. So let's kind of make a little inventory. First things first, I always like to say my object. So my height of my object is given to us at 6 centimeters tall. Okay, no problem there. Distance of the object, however, so how far the object is from the lens, that's unknown. We have no idea what that is, right? Next up, let's deal with the image. Height of the image. Well, we don't know how tall that image is, so that's an unknown to us too. Height of, or sorry, not height, distance of the image, however, so in other words, how far the image is from your mirror or from your lens, we do have that, 6 centimeters, but keep in mind, since it's virtual, we have to say it's negative 6.0 centimeters. The other thing, of course, we know is the focal length, and because it's a convex lens, which is a converging type of lens, we can say it's positive 4.0 centimeters. Ultimately, since we're looking for the magnification, we know there's the formula M equals HI over HO, there we go, equals negative DI over DO, right? So we have like a whole strand of formulas here. We can use either one of these, but unfortunately, looking at it right now, we can't use this far right one because we don't know what DO is. And we can't even use this one in the middle because we don't know what HI is. So we have some more work to do. The other formula we have with this is 1 over F equals 1 over DO plus 1 over DI. We're going to have to use this so we can find DO, because in other words, since we don't have DO, we can't use this formula. We need to find it first. Anyway, let's plug those numbers in because we can solve this because we have F and we have DI. So we got to throw those numbers in there. 1 over, I'm going to just ditch the 0.0 just to make things easier. 1 over 4 equals 1 over DO plus 1 over di, and di, of course, is negative 6.0, so I'll just say it's plus 1 over negative 6. Now, adding a negative is kind of bulky, so I'm going to change this now to 1 over 4 equals 1 over do minus 1 over 6. That might make it a little bit easier. Let's just add the 1/6 over to the other side. So we have 1/4 plus 1/6 equals 1 over do. Now, I don't know about you, but looking at this kind of just gives me anxiety. So I'd rather like change this so that it's one fraction. Now, when you're adding fractions to get them to have the same, or get them to add together, they have to have the same denominator. So a common denominator between 4 and 6 would, of course, be 12. So I can make this 3 out of 12 plus 2 out of 12 equals 1 over do. 3 over 12 plus 2 over 12 is 5 over 12, which equals 1 over do. If we're going to solve for do now, we just have to times by do, times by 12, divide by 5. So kind of like the cross multiply and divide thing. So do is going to equal positive 2.4 centimeters. And that's not what we're looking for, though. We just need this, so we can use this formula right here. So let's now apply that. M is going to equal negative di, so negative 6.0, double negative there. That's going to be pretty useful. Divided by do, which is 2.4, as we just found. So really, this is positive 6.0 divided by positive 2.4. You can throw that right in your calculator, and you'll find that M is equal to 2.5. Magnification has no units. It's just a factor. In other words, it's just something that you multiply something by. What you can interpret this as is your image is going to be 2.5 times taller than your object would be. That basically is what that means. Okay? Anyway, we're done. So for practice, any remaining practice problems in either your EMR Part 1 or EMR Part 2 booklets, just because we worked on EMR Part 1 today does not mean you have to just deal with EMR Part 1 questions. Keep in mind, Thursday's unit exams come around. It covers both of those sections. And just so you know, right now, it's going to be entirely written response. That shouldn't be a surprise to you. I've kind of been going more towards that lately rather than putting together something multiple choice. It takes less time on my part, and I think it's a better assessment because I can actually see what your work is. Multiple choice is not really ideal, not going to lie. I think written response is a lot better. Anyway, I'm going to stop rambling and wasting your time here. Give those practice questions a try. Hopefully it didn't take you too long to do this today. And if it did, or if you are still stuck on any of the things we talked about today, please send me an email, send me a remind. And if you want to book a one-to-one Zoom session, we can do that as well. Anyway, best of luck.